I'm in the Department of Mathematics, and we've heard a lot of really interesting and varied discussion today. And I think one underlying current is there's a lot we don't know, and there's a lot of uncertainty, which is what I love about mathematics, is we can explore what we don't know in uncertainty and look at some sort of what-if scenarios with different parameter values. So what I am going to be modeling today, and this is just a reminder about the Velella life cycle. So we're going to be looking at the Velella that live on the top of the ocean, and specifically looking at this species because they are really a foundation for the ecosystem. I'm hoping in the future to be able to look at then interactions with other species as well if the Velella population is affected. So the way that the Velella interact with the trash and the effect of interaction with the cleanup system and what potentially could happen to their populations based on those two. So we are going to be looking at two different life cycle stages. So the polyps are at the surface, so we're going to assume that they are going to be impacted by both interaction with trash as well as interaction with whatever cleanup system if they end up interacting with it. We have the medusa that are produced by the polyps that we do know float down some amount. We don't know quite how much amount. So if they float down below where we really see trash or below where we see these systems being employed, then we would have that they're unlikely going to be impacted. But again, we don't know that. So we're going to assume that in general the medusa are not going to be as impacted. But again, this is something we need to sort of look at in the future to see where do they live physically. So looking at their spatial scale and how they would interact with the different with the trash and with the cleanup. So this is a diagram of the model before I show you the actual mathematical model. So we have that the medusa, they produce polyps, and that the polyps produce medusa. So you'll see those birth rates are, if you've done any modeling, you're kind of used to birth rates from the species itself. So the birth of the medusa are from the polyps, and the birth of the polyps are from the medusa. And then we have some trash terms. So we have some input of trash, and we have some output of trash. And the output of trash, so we've talked a lot about what is this degradation of trash. So I'm assuming that we're talking about trash that is already in the garbage patch, and how often does it degrade, or in what time frame does it degrade. And I think I've assumed about 30 years is the time that it's going to take for it to naturally degrade once it's already out there. So the medusa and the polyps can die multiple ways. One, they can have some interaction with the trash. So again, it's very unclear. What is that interaction? What number of those interactions actually result in death? But we're going to assume there's some interaction with the trash that is negative. And then they do have a natural death rate, which is not shown here. So the way in which they're either naturally dying or are preyed upon. And then it is possible that they will be killed by the cleanup efforts. Right? We saw earlier that if we catch trash, we are going to catch Velella. And so we saw by the ocean cleanup this morning talking about the input of trash versus the trash cleanup. Right? Those are two things that I think we all agree that probably should be done. But the real question that I can't say I'm going to attempt to answer, but at least shed some light on, is where is that balance? Obviously, we only have a finite number of resources, and where should those resources be directed? Towards the import, towards the rivers, whatever that is, be it the interceptor, or be it further upstream, or reducing plastic production in general, or should more resources be put towards actually cleaning up what's already out there? Should it be half in between? Where is that balance going to be? So I had to start somewhere with these parameter values. We've seen a lot today that a lot is unknown. And so you're going to see later that these are just starting points, and they're going to show a lot of varied parameter values. So based on this 50% removal in 5 years, which has been talked about a lot, we look at a trash removal rate here. And then how are the Velella killed by the trash interaction? That's really hard to quantify. So I found a study on fish, and I'd really love to see you all would say you had more information on the interaction of trash with the marine life, and I would love to look into that more. So they said 35. They found plastic in 35% of fish. So that translated to 0.1047 rate, and my time scale is going to be in months. What percent of the Velella are killed by the cleanup effort? So the space is all based on a square kilometer, and we're assuming we're looking at Velella in the same space as where the cleanup is occurring. And so certainly there's a bigger question of where are the Velella in general relative to the space that's being cleaned up. And then their reproductive lifespan, it was sort of touched on earlier. Do they reproduce super quickly? Do they not? So we've looked at some estimates of the polyps living about 3 months, and the medusas living about 1 month. So we're going to assume that is their lifespan, which informs our death rate. And initially, we're going to start in equilibrium, assuming however many die naturally are going to be, how many are going to be put into the system naturally, make it to reproductive age. But we'll also look at varying that. Okay, what if they do reproduce really fast? What does that mean for this? So these are the systems of equations. So I've looked at it both as a deterministic system and a stochastic system with very similar results. So we have the change in the polyps and the medusa and the trash. So some assumptions that we're making here is that, first of all, we're really not looking at the mechanism. So we saw there was ingestion of trash and entanglement of trash. We're just saying the middle terms there, the PT and the MT terms, that there's some interaction, so that's a mass action. There's some interaction between the polyps and the trash and the medusas and the trash, and then they're killed at some rate depending on those interactions. So we're not really getting into the details of what is the nature of that interaction, which would be really interesting to look at. So those are the two parameter values we're going to look a lot at. So we have a natural death rate and some death due to the cleanup. So we're going to look at what, like, from 0 to some higher number due to the cleanup, what would the result be? Then trash removal, trash input. For now, I'm assuming that that the rate at which it is going in is constant. Again, that also might be a function of time and maybe increasing that we're seeing. For now, I'm assuming that the rate removal is constant, which also might change over time as we see as if we have more fleets go up. And then the trash degradation. So that's also a question. That one I don't really address as much in this, but really could be with similar analysis. So that this is the continuous system. So for anybody who is interested in quantitative model and really is dying to get into stochastic modeling, a colleague of mine has created a really easy interface where you can put the values in, and it will actually produce these graphs and some of these heat maps we'll see later produced from the system. So if anyone's interested in that and wants to know more about, please contact me, or I can put you in touch with the creator. The initial conditions were a little bit hard to figure out. How many polyps and medusa and trash should I start with? And so I'm really interested in playing, because you all said 180, I think it was 180 times more plastic than biomass. I started with a different study that had a 5-to-1 plankton to trash in terms of pieces. There's, I think, 6-to-1 in mass. And so it's a big question of should we be looking at mass or should we be looking at individual pieces? So I'm looking at individual organisms and individual pieces. So I did about a 5 to 6 to 1. Again, that was plankton and not Velella, but again, we have to start somewhere. So based on, and so this is just really just what you put in to the website, and it does a lot of the back-end calculating using the Gillespie algorithm. And this, what?
It's a website?
Yeah. Yeah. So this is just sort of the initial results of the model, but you shouldn't really take anything from these yet, because again, these parameter values, what are they? So but you can see in both the continuous and stochastic model, they have similar results of both polyps and medusa. decreasing over time in an area in which they're both interacting with trash and interacting with the cleanup system. So the first question is, what would happen with the polyp population based on a varied cleanup rate of killing them? So it's the cleanup system is out there, the Velella is interacting with whatever system is out there, they're dying at some rate. On the left, we assume that there is a negative impact due to trash interaction. And on the right, we assume that there is no negative interaction due to trash interaction. We don't know which one is right or if it's somewhere in between. And so this graph is not read the way you normally would think. It is so that the x-axes are the cleanup kill rate. So on the far left, we have 0. So meaning that the whatever cleanup, either there isn't a cleanup system out there or whatever cleanup system is out there has 0 impact on the polyp population. And the far right, we got to 0.02. And I've just put a little vertical grade bar to show what translates to that 50% in 5 years. And that rate is also making an assumption that you have nothing coming in and no degradation going out. If you just have 50% in 5 years, that would be that gray bar. So along the y-axis, that is the percent of whatever initial population. So it's not pure numbers, it's percent of wherever we started, what percent that would decrease to. And so you read over time, you actually read the bars vertically from the blue line down to the pink line. That is time. So for example, on the left, there is some trash interaction. So if you look all the way on the left, if you look along the y-axis, so blue, green, light pink, blue, and then pink again, that decrease is 100% going to be due to trash interaction. So it's unclear if that parameter value should be that high, should be that low. So just due to trash interaction, that's it going from nearly 1 to a little below 40% in 10 years. Is that likely since trash has been out there, they've been interacting with wood? Probably not, but again, we don't really know. But on the right, we see that if we have that the cleanup is 0, that's assuming they're not dying due to trash interaction at all. So you notice that if the cleanup rate is 0, they all stay at 1 because we're assuming the birth and death rate are the same, so they're going to be staying in equilibrium. So in both cases, we can see that if we just come just a little bit off 0, right, just a little bit off 0, we are going to see their population decreasing over time. Just for reference, I put the red dotted line to show you that that's 50%. So you can see on the left, in 5 years, that turquoise line is going to go to 50% in 5 years. And on the right, we're going to be down to 50%. So that's of the initial population. So same question we can ask about the Medusa.
Is that so you have a 50% decline in the polyps because you assume that they're cleaning up 50% of the trash?
Well, we're assuming that as they clean up 50% of the trash, they would also be cleaning up 50%. So this vertical line is 50% of the polyps is the rate equivalent to basically a half-life of 5 years. Yeah, because we're assuming if they collect the trash, they collect the polyps. Right. Again, what's the valid rate on it? This way we're looking at this sensitivity, right? From 0 to below it to above it. It's certainly not going to be 0, but how high is it going to be and what is that impact going to be? So because the medusas are created from the polyps, we assumed that the Medusa effect was going to be very low, and so when I ran that, all of these were flat lines, nothing changed. But if that was looking at, that was with an x-axis of medusas killed by the cleanup rate, because we assumed it was very small. But the medusas are produced by the polyps, so if a lot of the polyps go away, you're not going to have as many medusas. So the x-axis is the same as the number of polyps killed by the cleanup, and then the number of medusas that you have. And so if you don't have polyps, you don't have medusa. If you don't have medusa, you don't have polyps. Again, on the far left is you're going to read time from blue down to pink. And on the left is assuming that there is trash interaction. And so if there is, then the question is, okay, is the trash is killing them alone, right? If we don't clean it up, then the trash itself is, the interactions with the trash is going to be cleaned. Is that eventually going to go down really far? Are they going to recover? But the cleanup effort can kill it too. So is there some balance in between that we can find? And so that leads to looking at the birth rate. Can they recover themselves? So whether or not they're dying due to trash or due to some natural occurrence or due to a cleanup effort, what would their birth rate have to be in order for them to recover? And so for those of you familiar with the modeling, you will note that there was no carrying capacity in it, meaning we're assuming that it can grow exponentially if there are no limitations on the resources, which we do know is really not realistic. But since we don't really have knowledge of what a carrying capacity would be, we just want to look at where's this bifurcation point where it changes. And so what we're looking at, so on the x-axis again is the birth rate of the polyps, and the birth rate is relative to the death rate. So we assumed that the polyps had a 3-month lifespan, so we have a death rate of 1/3. And so we start with 1/3 is kind of our 0 on our x-axis, and we go up to 0.5. And we're looking at how much above the death rate would the birth rate have to be. So you would expect over time the population to increase if you have if your birth rate is higher than your death rate, then you would expect the population to increase over time, right? So on the left, we have, again, you read time from blue to pink, and it looks like that the birth rate would have to be about 0.44, which is about 1/3 higher than the death rate. Again, we don't actually know what this is, but this is just what it would have to be. So if we had the trash interaction and the cleanup were killing the medusa and the polyps at some rate, what would the polyps naturally have to do to recover? And they would naturally have to reproduce 1/3 faster than they naturally die. Is that feasible? I don't know. If you look at the same model, but without, if the trash is not killing them at all, you get about the same. I think you get about 30% instead of 33%. So the medusa are very similar. So the birth rate of the medusa would have to be about 35% higher than the death rate of medusa in order for them to recover, in order for it to switch from decreasing over time to increasing over time, right? You expect from blue to pink the population to go up if the birth rate is high. And so that you can see where that happens in both of these graphs. So based on the stochastic model, this is really, I think, a really big question for all of us and for the ocean cleanup is, where should those resources be? Should they be towards cleaning up rivers, or should they be towards cleaning up oceans? Should they be somewhere in between? So in this graph, so this is a heat map, and so along the bottom you have the rate of the polyps killed. So we have anywhere from 0, but they're not killed at all, to a rate of 0.007, which is equivalent to 50% in 8 years. So it's a little bit less than that 50% in 5 years. On the vertical axis, we have the input rate. So if there were more efforts put into decreasing the input rate, again, that could mean a lot of different things. Input of trash into the garbage patch. So this is not necessarily into the ocean in general. So I'm specifically looking at where the Velella and the trash are interacting with the potential cleanup. So this is input. So again, there might be some time delay. We've talked about the time delay from when it enters the ocean or coastline and when it would actually get to the garbage patch. So the numbers, I've just highlighted the 4 corners. Again, this is the percent of the initial polyp population that we would have after 5 years. So in this case, red is better, because if you want to keep the Velella, red is better and blue is worse. So in the top, we have 68% or 58% of the initial population, and on the bottom, we have 37 or 38% of the population. So the top left is unrealistic that we'd ever actually get input to zero. Are we ever going to get trash input to zero? No. But that would be, in a perfect world where we could get rid of all of the trash going into the ocean, but we do nothing about what's already in the ocean. It's going to be the top left. The top right is going to be the opposite. Not that we do nothing, but we do a lot less on what's going into the ocean, and we do more on what's already going to be out there, assuming that whatever is out there also is going to affect the Velella at some rate. So we can see that the gradient changes a lot more with an increased input, or if you read it from bottom to top with a decreased input. If we're able to decrease the input, we see that the gradient actually changes a lot quicker than from left to right. So from left to right is increasing how much we're cleaning up. Questions about this? Going on? So this one is the same idea, but just with the trash. What is going on? So if we, again, the bottom is the existing trash being cleaned up versus what the input rate is going to be. In this case, red, since this is how much trash is in the ocean, red is bad. We want more blue than red. So this is the numbers in the corners are just example values of what percent of trash from what we assume we have today to, and this is again just in 1 square kilometer of the garbage patch, so it might change based on the location, what we have today, what percent we would have in 5 years. So in the top left, we say we have 51% of the trash, and say on the bottom left, we'd say we have 1.4 times the amount of trash that we have now because it's coming in. And so again, so on the far left top, that would be that the input rate, so we have a more realistic of not of zero. That would be focusing more on the input, so more on perhaps river cleanup. And then the bottom right is going to be more on oceans. So you have more cleanup and less rivers. And so the answer is somewhere in between. And so again, the gradient here from left to right is not very strong. So as we focus more on the trash cleanup rate, the gradient doesn't change very much. But as we focus on the input rate, again, we need to kind of look at what the appropriate units of trash cleanup are. Is it pieces of trash? Is it tons of trash? Is it by mass? Is it by pieces? So this is really just a sample of sort of values that could increase, and we can see. And so, the reason you would have some degradation over time, and so the trash would still decrease over time, even if we have nothing. So some questions that we have to try to answer for better modeling. So is first of all, what are these actual birth and death rates of the polyps and the medusas? Can they reproduce so quickly that if we kill a lot of them that they're going to reproduce? Because that is really helpful to know. Or can they not? If you get them down to a critical number, are they not going to end up recovering? Should there be some consideration of carrying capacities in the model? It seems like we're probably not hitting them at all, so it may not matter. And a really, really big question is how the existing trash affects the populations. And so, I mean, just to say that it does, but finding like fish with plastic in them, does that tell us that they're dying due to the plastic? Somehow trying to quantify that somehow, I understand that would be exceptionally challenging, but if we could find more information on how that existing trash is affecting the population, and having some better estimates of current trash input, and I say better, the ocean cleanup has done amazing work to quantify how much plastic of different types is out in the ocean right now, but unfortunately the historical data is not really consistent. And what we can estimate is the best we have, right? We have to estimate based on historical data. It's not super consistent. And so how do you get a better estimate? I don't know, wait 10 years and see what happens and do nothing? That, that doesn't sound like it's the right solution. But, or do we estimate from how much is actually going in? You're saying that the 1,000 rivers and 80%, can we estimate how much is going into the coast and then estimate how much would actually move out to the garbage patch? Could that be an alternative way that we figure out how much this input is coming in? So those types of information would really help inform a model like this, or really any modeling efforts, significantly. And some questions for further explanation that I tried to at least open the door to, that I think we've been talking about all day, is, will existing trash cleanup or reduction of new trash be more effective? And so we have, like, yes, we want to do both. Yes, we don't want trash out in the middle of the ocean. Yes, we don't want more trash going out into the middle of, going anywhere in the ocean, not even just the middle of the ocean. But if we're going to put a lot of resources in one direction, is there one direction that's better? Does it have to be both simultaneously? Should it be cleanup first and then rivers? Should it be rivers and then ocean? I mean, there's a lot of questions going on there. And obviously, I'm simplifying of, like, how is this all done, right? How do we actually get it? How do we go out, and really effectively decrease the amount of trash going into the ocean to begin with? That's a lot of local areas to look at. And are there other, and I think there was discussion of this earlier about the size of the nets or the size of the mesh, or are there different ways that could minimally affect these populations? If we're trying to go out and clean up trash in the middle of the ocean, can we look at alternative ways that would decrease that, so that, if we know the birth and death rates of the polyps, can we get to a value that we find more suitable, that we're we're confident that they're going to recover even if we reduce them by some amount. If I'm happy to take questions. Put my contact information. I put a lot of hyperlinks in this slide. I think we're working on making all of the slides available, but if you want, if you would like these in particular, feel free to contact me. I know not everyone has access to Mathematica, but I've linked the model and the graphs that he used here, as well as a link to the Stoke SS site as well. So thank you, and I'm happy to take any questions now.
Thanks for the presentation. I understand there are a lot of uncertainties involved. The good news probably is that if the previous speaker was correct, then the rate is not that feasible, so it makes your calculations like an upper bound. Because I understand now that this 50% in 5 years is probably not feasible. This means that the rate that we have used is probably lower than that.
Yes, so it's possible. Yeah, that we're looking at a much lower.
I have now a comment based on your previous slide. I want to be like a bit optimistic as well. So I've seen, at least on Wikipedia, because I'm not much familiar with this GPGP, it looks like 90% of the mass objects are like larger than 0.5 centimeters. And again, according to Wikipedia, this Velella as an adult is between 40 and 80 millimeters. So there are obviously ways to find, alternatives ways so that we don't kill them all. Yeah. So that's the good news. Now, I'm kind of like convinced that we are killing though some of them.
Yeah.
And I've worked a bit on oil spills in restoration, and at least in the US, the Environmental Protection Agency, if there is an oil spill, they ask the company who is responsible to actually do what they call a habitat restoration. Now, based on that, I think it's very useful for any company that is doing this thing like removing all of the gases, and I think you and Rebecca could work a bit on that. You could probably estimate the number of Velellas that are being killed and how they can actually restore them. Because I have a good idea, and please don't laugh with that. At the same time that you're removing the garbage from the ocean, you could have like a facility there that could reproduce Velellas, if it's possible. So, have you done any research, like both of you, on what is the rate of reproduction so that there is like zero net effect on the population. I mean,
So
we are killing some, and at the same time we try to.
yeah, so that's what these were showing of what, I mean, we'd have to do sort of a parameter analysis, a more sweeping of all the parameter analysis, but can we, if we can establish what an estimate of how many actually would be killed, based on whatever system there is, then an analysis like this could show us what would the birth rate have to be. But I think you're also talking about reintroducing Velella into the system, which I mean, it's not non-trivial to introduce sort of captive bred animals into a wild situation. So that is an interesting suggestion.
That is definitely what the EPA is doing with habitat restoration. I mean, when we have an oil spill and you kill like 10 birds, they ask you to introduce like 10 birds to the environment.
Yeah, but again, so but this is kind of back to your previous comment on another speaker about the economic impact. The oil spill, right? They're out there to get oil for human consumption, to run, to do things, and they have a spill by accident, right? And then they have to restore the habitat. And we're looking at, and so the risk of, you know, the drilling for oil was seemingly considered before they were allowed to even drill. And this is similar to our conversation this morning about international law. What risk is acceptable? What is significant damage? For someone that's not trying to create a positive economic impact, they're trying to create a positive environmental impact. And so if you're simultaneously, and so that's where I think the question really lies. You're trying to create a positive environmental impact by decreasing plastic from the ocean and making it safer for the marine life that's there, while creating a negative environmental impact by killing animals that are already there. Where is that balance? And that, I think, really needs to be thoughtfully considered differently than the way an economic impact, that is going to be compared to an environmental impact.
It might not make any sense if you do cost-benefit analysis for that area. It might make sense in the rivers. I mean, I do agree with that. If we place a value on the benefit from removing plastics and on the damage on the Velella or the other micro.
Right. I mean, well, your benefit could be helping certain marine life and the cost.
This kind of economics. Yes. But if they actually say, if they approve this thing and it operates there and it damages and we can assess the damage, then I assume that they have to be forced to restore the habitat loss. That's why I said that, I mean, which is common practice in the US.
Yeah.
They're already doing that, presumably, by removing the plastic. So they've got a budget, they've got a bank of how much they improve the environment by removing the plastic. The risk that the impact that you're talking about should be attributed maybe to discount that, but not additional things.
I'm talking about the Velella because if they kill 10, they have to introduce 10 to the environment.
Yeah, but it could be the case that they improve the environment because they've taken out the plastic. So there's a discounted perhaps, but not an additional payment.
So you were thinking more of the proper Amazon burning down rainforest farming that the indigenous people did. Burn down the patch and let it regrow. So if I remove Velella and they can regenerate and have a better habitat, didn't I do something good? Is that the argument?
No, that's not the argument.
Okay.
Although that is an argument. There are, biology is very complicated. There are compensatory mechanisms. There's density dependence. So it could be the case that you can remove a lot of the Velella and not make any difference at all with the Velella population. It's really quite hard to say. But what I'm saying is actually quite different, because you were saying that, well, they have to be held accountable for the damage they're doing. Well, but they're out there doing good overall. They're not creating economic advantage for themselves. They're doing good for the environment per se. And so let's say that much. And if they damage the environment in doing that much good, then whatever that damage is has to be taken from this sum first. Maybe it's in aggregate negative. Maybe the damage they do is more than the benefit they create. Or maybe it's just a portion.
I do agree with you, but
or maybe it's nothing.
At least the last previous three speakers, they don't seem to agree on that. And I mean,
So I think that if replacing Velella would be extremely challenging, right? Like we struggle to grow them on a small scale. So like all the parameters that Megan used in this talk for like birth rate, death rate, and stuff like that. Those are all like very hard-won parameters from like very much experts in the field, like working to try to determine those numbers. So it's not a matter of like you just get a big swimming pool and eat up a bunch of Velella and they'd be great. And I mean, I think it's I wish if it was that easy, like my whole career path would be totally different, right? Like, so I don't think that would be possible. No. But I want to. Can you go back a little bit? Because like, I know. Okay. Go for it. Okay. So I just want to try to make sure I'm sort of clear. So like, so what you're saying is like based on cleanup and trash interaction, Velella with the current reproductive rate that you have from the literature, both medusae and polyps, would need to reproduce like 1.3 times as much in order to stay the same.
Yes, yes.
Okay, so like what would
if the trash and cleanup assumptions I have a big if, you know, and obviously you can put different ones, so it'll be a different graph. It might be 20%, maybe 50%.
Right.
But yeah, based on.
And then the percent initial polyp versus cleanup kill rate without trash interactions.
So that's we're on the right. That is assuming. Okay, so say that the trash is not killing the polyps.
Yep.
Like saying that trash interaction, that not that they're not interacting, but that interaction is not causing a negative effect.
Right.
Then the right side is what just from the cleanup would be.
But this includes because I think you were asking a question about like it's about 50% after 5 years. So and is that because trash cleanup is 50% after 5 years? But this also includes reproductive rate.
Yes.
Right.
Yes.
So it's 50% after 5 years, including the fact that they're reproducing.
This is assuming an equilibrium reproduction.
Yeah.
This graph is. They're not reproducing at 1.3 in this graph.
No, but they are.
They're
the
reproducing.
reproductive rates that we sort of scratched from the
they
literature
are still reproducing. Yes.
Are incorporated into this.
Yeah.
So it's not just a matter of like 50% of polyps are cleaned up because they're sort of at static state. Like 50% of polyps with realistic reproduction rate.
Yes.
In the area that is operating.
Right. Exactly. In the area in which this is operating.
Yeah, I would have to go through your slides slowly again, so maybe the question is answered with the slides. But the cleanup rate, is that you're looking at different rates of how much trash you're removing, or how much
this is
together with the.
So this is, I don't know if this. So the cleanup rate. So these last terms here, we have some percent of polyps. Some percent of them are being killed due to the cleanup, and so that rate is translating from this set of equations here. So that DPC is going to be the death rate of polyps due to cleanup, and so that's our cleanup rate. So it's strictly polyps times that. So there's no interaction.
So there's no. Have you looked at like different ratios then of so when you change the cleanup rate, is that evenly impacting the amount of trash you're taking out and polyps? Or is
you're looking at you're looking at the trash. Sorry, you're saying the trash removal versus
exactly.
Yes, I have that dynamically as well. That I guess I can pull up if we're all really interested in looking at.
Yeah, do you have it?
Yeah,
the polyps are killed less if you include the trash interaction.
I think it was
no. Including this far left here. This far left here is if there's no killing by cleanup, you would still have that trash would be decreasing the population.
Yeah, but if you remove the trash, then you reduce the kill of the medusa and the polyps.
Oh, do we reduce? No, in those particular graphs we have.
So you kept that constant.
We kept that constant, and so that, but I don't know. If I take a minute here, we can change them all at the same time. So.
Did you have more questions, Andrew? Can I ask a
Yes,
question?
absolutely.
Because I know a bit about stochastic modeling.
Mm-hmm.
And maybe it's a question that's more applicable to a quantitative ecologist. I don't know. They are in the room.
Whoa.
Yeah. But I know in stochastic modeling, everything changes when you introduce correlations.
Mm-hmm.
And especially in the life cycle of a Velella, I can imagine that there are correlations. That between death rates of the polyps and a birth rate of the medusa, or vice versa. I mean, there must be examples where, because of the imprinting or whatever of organisms, that they reproduce faster when something is upsetting the balance.
Yeah, so I can only speak to the numbers that I found and then deposited. So the medusae appear to live 1 month. They reproduce once and then they die. So that was sort of incorporated, and then the polyps live, somewhere between 2 to 6 months with an average of 4 months. And so you would expect catching polyps, the rate of medusa production would then go down, follow it quite quickly, because those are totally correlated. The number of polyps and the number of medusae, I mean, it's directly related. Is that what you mean?
It is what I mean, but that can't be right, I would say, because if it's always constant,
what's always constant?
One way you might address it is to ask: is there are there huge differences in concentrations of Velella across space? If there are some places where it doesn't grow, that's fine. But if there are places where it grows and really grows,
right,
very luxurious, and other places where it grows, but it's like half that amount or
right,
that amount. Does that exist?
Yeah. So I mean, there's definitely, I think, because so we don't know about the medusae, but because the Velella have a little sail, they have a little bit more of a windage term, and so they do seem to be probably one of the more widely dispersed of the Neuston, which is also why they're the most well studied of the Neuston.
But they're not going across the ocean, are they?
I would think not.
They've got big
for
habitats.
For both time purposes and, it takes more than 4 months for a tiny animal, even if they were being flown directly across. So there is an unpublished master's thesis which does show preliminary data on genetic structure of Neustonic species, and there is some evidence in that they're not just uniform, among different gyres, that there appears to be some isolation for some Neustonic species within gyres.
So I'm really asking, are they K-selected or R-selected?
Oh, good. Well, I think that in order to answer that question, you have to have death rate, right? So the reality is the parameters that we found were they produce between 10 medusae a day to 200, I think, was the maximum. So those were 3 different estimates from different experts, sort of bracketing those extremes. And then the medusae, we estimated, produce about 12 to 15 eggs, which is the limiting gamete in reproduction, and then they die. So, yeah. Yeah. So if there is K and R selection, it's different between, because medusae are being produced. No, I'm not totally sure about that. I think I just learned something very personal about you. Well, so this is pretty classic for jellyfish, right? So you can have either asexual reproduction in large amounts or sexual reproduction in large amounts, right? And so those estimates of asexual reproduction, which is the number of medusae, that might be a larger number, and then each medusa only produces a small number of eggs, right? So that's where it gets complicated with these complex life cycles.
Matthew,
so yeah, this is kind of a follow-up to Lonica's question about stochasticity and correlations. Am I right that in each simulation the parameters are treated as known and the stochasticity comes from exponential waiting times between discrete events? Is that
yes,
right?
Yes.
So effectively what you've got is just demographic stochasticity rather than fluctuating environments or fluctuating demographic parameters in the environment.
Yeah. And so
that's where those data that I showed from Vortex Swim could then be folded in. So I'm thinking about what we're going to do like for the next few days. I think if you wanted to include spatial variability, that's where you would get this data.
And I just, for interested, pulled up, because you were asking about the trash versus the cleanup. We can dynamically look at some of them, what would happen if the rate of trash removal decreased and the cleanup death rate decreased. What would we have in terms of what the population would be doing? So if we have, trash removal is low, obviously the trash is going to stay. That's a percent of initial with a very low input to the system. We can look at if we input the system, right, even if we have that the cleanup death rate, if the trash is super high, if the trash input is super high, then we can see the green graph, that's the amount of trash that's going to go off the chart, and we're going to kill everyone because there's going to be so much trash that it's going to be killing.
This is what it was like to play.
Yes, yes.
Something happened in mathematics when I was watching. It's supposed to be hard.
So what happens if like their interaction with trash death rate is lower?
If their
This, I think, is like,
rate,
yeah.
polyps killed by trash, yeah. So if that's really low, even if you have a ton of trash, then their population stays a little bit higher.
And that is only affecting the background situation without cleanup, or also the.
So in this case, let's see, the cleanup, I have this. In this case, this is zero cleanup. Yeah, if there's no cleanup.
But if the cleanup was higher, is that then also
if the cleanup is
killed by
higher,
trash rate, is that also inside the system or by the cleanup effort? No, that's only the other parameter that is there.
Yeah, so I've not specifically linked the death rate due to the cleanup and the actual rate of trash removal, and so those may be the same, may be different. Yes, I started with them the same value. Likely that they're not going to be identical, so we can see what's going to happen.
Same with the removal rates. That's
exactly. Removal rate is so. Yeah, the parameters are not specifically linked. So I'm hoping to do like a more substantial parameter analysis of like when you're moving multiple of them, what would the output end up being? Question?
So you're in all of this, you're assuming that as soon as a polyp dies, every third polyp produces an additional one. Like 0, if there would be new polyps, 0.33. So what's the growth rate? Are you talking of an equilibrium growth rate where every dead polyp produces one? Or how much?
Well, we're assuming that for every polyp that is removed from the system naturally, a polyp is produced in the system naturally. Does that mean a 1-to-1? Maybe not, right? Because they could produce 1,000 but only one make it. Yeah. Something like that. So what the actual mechanism is not incorporated into the model. It's just we're assuming if they're in equilibrium, and we can see, for example, if we increase the birth. Oh, wait, okay, that was too much.
Very well.
If we increase, the birth rate to a lot higher, we get different results. So
because if I remember correctly, a lot of ecosystems should have some effect like this. If I reduce the number of the population, growth should rise.
Yes.
Something like that.
Should it? Does it?
Yeah.
Unclear. What? And in order to really properly analyze this, we would at least want a better idea of what this value is.
I think it's time we should conclude. I wanted to thank you all for let's thank our speaker.
Thank you.